friends to our PCS-IBS seminar. Today we have the pleasure of hosting Dr. Chae-Yeun Park from Xanadu Quantum Technologies in Canada. And our scientific host today is Dario. And please, Dario, introduce our speaker.
Yeah, thanks, Dylan. Yeah, it's a great pleasure to have here Chae-Yeun, who is visiting us just for today. But yeah, we had the chance to have him, and I think it's the first time that we have a speaker not coming from an academic environment, but from a company. So it's nice to start, let's say, a new trend. So let me introduce our speaker. So Chae-Yeun got his PhD in Seoul National University in 2017. At the time, working on quantum optics. Right?
Kind of later. A little America.
Okay. After that, he was a postdoc in APCTP in Pohang, so not that far from Daejeon, which he was working in the quantum information and many-body theory group for essentially a year. Then he moved to Germany, in Cologne, and he stayed there for 3 years. And after that, he joined the Xanadu Quantum Technologies in Canada, where he's now working both as a software developer and a quantum scientist. Now, his research interests are, let's say, related to quantum machine learning, quantum computing, simulating many-body systems on quantum computers. There we can see in the background a quantum computer that they are developing at Xanadu. So now his talk will be about part of these developments in Xanadu, and the title is Fine-Grained Complexities in Parameterized Quantum Circuits. Chae-Yeun, I think you can start.
Thank you so much for introducing me. So I'm a scientist as well as a software developer in Xanadu. Yeah, as Dario introduced, and yeah, as Dario already said that this is our the computer, like a version 0.1 maybe. Yeah. So let me introduce a little bit about that because people here may not be much familiar with what the quantum industry is doing. So we are a full-stack quantum computing company. So we do also software and hardware, and we build chips so based on quantum optics. So we aim to build a tolerant quantum computer using quantum optics. So all these devices are actually like a classical controllers. The real chip is really small. It is like your thumb there. And all these attached things are like controllers. They have like a classical purse, and we have to learn these things. Of course, I will not say anything about our hardware today. Yeah, my topic is fine-grained complexities and parameters.
So can I ask, are those wires, are they all fiber optics cables?
Not really. Some are, but yeah, most of them, they are more like electric cables that controls the pulses. Yeah. Okay, focus is lost. So first explain classical chaos. Of course, most of the people here are more familiar with this than me. So in general case, classical chaos is often defined as a positive maximum diagonal exponent. So when you in the base space, in the classical base space, you just move in the unitary condition a little bit. However, the trajectory after some time becomes really different, then we say it's chaos. So it also sometimes indicates some recalibration, and all these things are quite weird. I mean, I actually like a chat with mathematicians who are defining classical integrability, and they actually said that even classical cases, it is not very defined, but I would say it is more well defined than quantum cases. So this is the base picture of the classical kick rotor, so rotator, like the spins with just a kick time to time, and how this base actually behaves. And depending on the strength of kick, it actually like this random type of reason grows. Here it is more like a regular, so the point here just to move around the sucker. However, like here it's more like noisy, which means that after some time it moves to somewhere else. So more like a randomness develops. Yes. Following this notion, people tried to define a quantum chaos, and yeah, some people have some definition, but yeah, what I would say is that they are not really well operate between fields. So, for example, a quantum opticians usually say the phase-space delocalization. So they can look at this support semi-Q function or a singular function, and yeah, in some cases, yeah, you can actually see something like a pleasure chaos also observed in this functions, this quasi probability functions. So this is an example. They implemented this kicked rotor, the quantum version of kicked rotor in some experimental system, and they looked at the same function, and they actually this is a time step, and after times it goes through all of the phase space, and this, yeah, some people call this is a quantum chaos. And another notion of quantum chaos people have looked at quite intensively recently is that thermalization. So, yeah, as I said, if a classical system has a chaos, then it doesn't really conserve anything other than energy, and it is often related to this summary equilibration or the thermalization. And even for a closed quantum system, you can define thermalization. Then in this case, yeah, you see that this time average of some observer is close to be approximately close to the microcoulomb per ensemble value. So it is also one of the notion of quantum chaos, people say. And the last thing is that the operator spreading, it's more from kind of physics, I would say. Yeah. It is also well defined for random circuits. However, yeah, and it is less well defined for the usual Heisenberg, the usual Hamiltonian equation, local Hamiltonian equation. However, for yeah, this is wrong reference. Yeah, this is a picture in quantum circuit operator, localized operator develops after time evolution. So this is another version of chaos. Yeah. So we, of course, I mean, definition is not really of course, definition useful, but we want to really check whether our system has satisfied those notion of quantum chaos. And one way to diagonalizing, especially thermalization, is testing this other eigenstate. So you can numerical construct the Hamiltonian and diagonalize it, and yeah, check whether this condition is satisfied, which is occurs the diagonal 88. So it's a diagonal version of the eigenstate thermalization hypothesis. Yeah, and people really did this many times. Yeah, so yeah, this is a pretty hardcore boson Hamiltonian, yeah, Ising Hamiltonian for hardcore Hamiltonian, and you see this for a specific observer how this behaves as a function of n when n is each eigenstate, and yeah, even as a function of this energy. So you see that it's rather smooth, and as n increases, the fluctuation actually decreases. So this is how people usually understand chaos in this notion of chaos thermalization in quantum system. Yeah, of course, you can see another different notion of quantum chaos. So, yeah, some interesting fact. Yeah, people got really interested with, yeah, or several years ago is support out of time for later, and this is defined like this, where rho is an average. The real definition actually the root comes in as a caret here and there, but yeah, those details are really important for me. Yeah, what I really use is it is dependence this, and where ut is given by this time evolution. So if this quantity behaves like a so if this quantity decreases fast, then people actually say that there's operator spreading. Yeah. However, yeah, for me, what I see is that where So this not this out of time collector is more like a defined for the black holes and or this highness speed paper. But of course I don't know black hole, and this is my black hole. So where U is a type of random unitary from Harlan. So drawn from ensemble, and where L and A and B, ins and C and D actually comes out. And sometimes B can be called as black hole and B can be called as a photon radiation. So this is a kind of simple view of quantum chaos for quantum information theorist. And if for this vast, so for the vast granular, like a black hole, people actually found that this quantity, this time collector actually indicated exponentially small to n, where n is the number of qubits in this actual case, but in general, like the dimension, the scale of the Hilbert dimension. This is what we know. So by just looking at this, we actually can say that how much U is close to the random unitary, and this can be a notion of chaos.
Which quantity is this quantity?
Sorry, so this quantity, this one. Where V and W are.
But it's a function. So
so
0, it is 1, and
here, here n is the number of qubits. So I'm actually thinking about like a spin chains, for example. Spin chains. And the number of spins are the same.
But it's a function of the time. So
function
there's a scale at which it becomes exponentially small.
Right. So
that scale is the important thing.
So the scale, as a function of t is also important, especially for example, like it distinguishes the interaction ranges. For example, like SYK model, it grows exponentially, but in this case it decays exponentially. But for local Hamiltonian, it never decays exponentially. So there is a difference. But for here, I only focus on the limit that t is much larger than 1. So the converged value. However, the problem is that real hard random unitary is unphysical. So, in some sense, you cannot implement a real black hole in a quantum for arbitrary n, because to do this, you actually need an exponential large number of gates. So this is what this paper actually says. However, one point is that instead of purely like building a unitary, hard random unitary, you can just think about the approximation of parameterized, which actually gives the same moment, same TIS moment. So this is how unitary T design is defined. It's more like quantifying a randomness of your unitary. So this is really drawn from hard random V. However, in this case, you're thinking about a class of ensemble of your unitary. And even in this case, the other two quantity can be equal or like approximately equal. And in this case, we can say that the unitary T design.
So,
sure.
if you can go back to your cartoon of black hole. You explain what are those A, B, C? I mean, what is the purpose of it? So like how can I see that this is a black hole?
So it's more like a particle comes into black hole, and after some time, it actually,
so it's like particle, something falls in and the other one gets out.
That's right. That's right.
But then does it mean that your A, B, C, and D, like these have to have certain, like what are you sending in? What is coming out? How do I see this? What is the analogy?
So you can think about total radiation as So if information is preserved, let's assume that, then if a particle comes into black hole, and after when black hole really evaporates, the same information actually comes out.
Okay.
And that is what B is.
But the nature of A, so if I understand it correctly, A, B, these are like some qubits, right?
Here,
and then you are doing some unitary operation on them, and then those are the outer channels that are coming out.
Yeah.
So then, what property, for example, D has to have so that we can call it a Hawking radiation?
Yeah. So one of the I would say it is more like a toy model. Yeah. So if you really think it as a black hole, then there might be some problem. But yeah, what we can say is that we can actually recover information from this Hawking radiation, and this is called the hidden Pascal protocol. And yeah, in that way, they actually have argued that you collect all the information from the black hole when it evaporates, then you can actually construct all the information of particles that can come into the black hole.
But at least the number of qubits that goes in B should be equal to the number of qubits that come out in C, right?
I would actually think that B and C are the black holes, before and after.
So then
I think that okay. I might. Unfortunately, we are on YouTube, so I should be careful of what I'm going to say. But I think more or less the idea should be that initially you have a product state in which you have one qubit, which is A, and then multiple of qubits, which is the black hole, and you have a product state like all the rest and the single qubit. Then after this unitary evolution, you end up with a new state which is not a product state anymore.
Okay.
Say the Hawking radiation and the black hole are entangled. And so the idea is that how you reconstruct the initial information of the qubit A out of what you can read from the Hawking radiation that is coming out. Which is a complicated problem, I think, because what you get is highly entangled with the. So you start.
It will depend on you also. It will depend on you.
Right. And in this paper, if I remember, Hayden and Preskin were assuming that U is randomly starting from the unitary, from a random. They were arguing how much information you have to know about the Hawking radiation in order to fully reconstruct the initial qubit. Something like that. Okay. Yeah. I apologize if I said
Okay, but I have some questions.
Yeah, so for contact information series, we usually don't really care too much about the hard random unitary, but we mostly care about unitary T design or tools, like usually 2 or 3 decimal for most of it. Yeah. And if you go back to the form of the outdoor formulator, it has actually 2 U dagger and 2 Q and 2 U dagger. And for our unitary operator that actually satisfy the 2 design, it actually goes to be exponentially small. So you don't really need to make out of time formulator small. You don't really need a full unitary. You just need a unitary 2 design.
What do you mean by the circle with the cross?
I'm sorry.
There's a circle with a cross. What do you mean by that?
This one?
No. Circle cross T.
Yeah, this is the T, like the tensor product. Yeah, times T.
The same U theta?
Yeah, the same. So this is just a slide for analytical expression of how it works. So what people do is that we already actually know the analytic expression of this unitary T design, and what people do is that actually check whether the ensemble of your circuit actually give the same answer to this. So of course the details are not that important. And the minor notion of some simple quantum randomness I would explain here is that support.
Sorry, one question. So we're choosing ensembles of that U in that.
Yeah. So ensembles by unitary. So it doesn't really need to be hard random. It's just a unitary item.
Our random matrices are denoted as V. Yes.
Yeah.
Okay.
Yeah.
Okay.
Yeah.
And then you had an A in between. What is A?
A is an arbitrary operator. Arbitrary
Okay.
operator.
So that bracket dot thing can be any arbitrary
Yeah,
operator.
yeah.
And what is that arbitrary operator in the original cartoon? What does that appear?
I mean, yeah. You mean here?
Yeah.
Yeah, you can just think about it as a quantum state. A like an arbitrary operator, but then the operator also works like a so this also can work.
Okay.
Yeah, so the last syntax quantum like a chaos or quantum randomness, I would say is that the support photo-Thomas distribution, especially simple for quantum circuits. So if U is totally random, random, then the output distribution given by this, first you need to take the square here, sorry, follows this photo-Thomas distribution. So what it means is that Px is set, but if for all different unitary, for given x or like some random x, you just collect this probability distribution, then P is there should follow this type of distribution. So it is the support photo-Thomas distribution. So it is also from random matrix theory. Yeah, and yeah, this is by the paper by Google, and yeah. And this this blue curve actually shows the photo-Thomas distribution, and R is the noise rate of your circuit. So what is known is that a random quantum circuit follows this photo-Thomas distribution. However, when there is a noise, it actually deviates from the real photo-Thomas distribution. This is indicated by different color. And basically, what Google did in their experiments is that in some error rate, they actually like found the distance between KR diagonals and the distance between the photo-Thomas distribution and their output distribution from their experiments, and compute the distance between two. And they found that the distance is quite, it was quite big, but they could claim that it is still there is a statistically, you can say that it can be controlled in the way that you can say that your probability distribution actually has some signature of this photo-Thomas distribution. So basically, what I mean is that we often consider this photo-Thomas distribution as a signature of supremacy type of distribution. So if your circuit gives some type of quantum advantage, then the output distribution often follows this photo-Thomas distribution. So there are some cooperative definition of B U zero. Yes. And that's basically what we have. Okay, so so up to here we introduced lots of different notion of quantum or like a simple quantum chaos. And
sorry.
Yeah.
Can you explain why is it a signature of quantum supremacy?
The real answer to why is rather difficult. I think it's more subtle. It's what I would say is that for our
that if you can design, if your problem can be solved by a random matrix, then you can have quantum supremacy.
It's more like if you design any like a quantum circuit with quantum advantage, then they happen to follow this pattern. So there's no exact reason why. I can say a bit like detail later. So what I know is that the relation between those, So for example, like we know that summarization is not really sufficient for unitary design. So if you are summarizing local Hamiltonian, then what you usually have is that this time average is more like a summer average, microcanonical ensemble, or like a its canonical ensemble value. So in real unitary design, this must be like a trace O divided by D. So when infinite temperature, it is satisfied. However, if not, then it's not really exactly unitary 1 design. And also for unitary 2 design, so yeah, if your unitary satisfied unitary 2 design, then it was doubly exponentially small. But yeah, this paper actually proved that this is only the polynomial extent. So there's also discrepancy between those notions of chaos here.
What is the relation between these two lines?
Sorry?
What is the relation between these two lines?
Not really. So what I would say is that they are this unitary is not the unitary design. So they are deviates from. So this is for the first moment, and this is for the second moment.
Basically, W can be one of the O's. V can be one of the O's.
Yes, so here VW are just some
operators.
operators. Yeah, some operators.
So,
Yeah.
who is the number?
Operators. Yeah, you only have one operator. In the second line, you have 4 operators.
Yes. Yeah. However, like if they are unitary design, then we already know the value. However, it actually means that this property actually says that they are not really unitary designs.
Because you say if let's say e to the IHT were a unitary design, the long were an random operator.
Yeah, that's right. So
if it were a random, then this expectation value should be the same of what, of trace of O.
So yeah, it is actually given by.
Oh, I see.
Yeah.
So the fact that it's not really an random.
Yeah.
I see. Goes into the fact that you have a temp. Okay, so the effective temperature can be thought as a lacking from the unitary from being a random.
Yeah. I see. Yeah, kind of. Yeah.
And as a function. So,
Yeah,
so you're saying that the goal talk would be a polynomial for physical.
Yeah, for physical local Hamiltonians. Yes. Yeah.
And you say something about 2 design. Previous few slides ago, saying
right.
that it's 2 or 3 designs enough for exponential.
So for 2 design, what those people, PQC, like this particle PQC must be like exponential, doubly exponential. However, here you only see the polynomials, and the real polynomial vector is a bit complicated, but it's anyway polynomial. So there's deviation from the thermalizing Hamiltonian and the real unitary design, like half the unitary.
So we can say that a random is even more thermalizing.
Yeah, you may say that. Yeah, it's okay. Of course, random is even more random than thermalizing.
Probably exactly. Yeah. I mean, you say it's not the most terminal. No, exactly. Yeah, that is the point. SYK will take the Hamiltonian SYK is not a unitary, right? It's not a random unitary. Yeah.
It's not hard, but what people think is that it's much more like a parameter. It is not. It is different, but the point is that it is not really local Hamiltonian everywhere. So it actually gives some properties of local Hamiltonian. So it's one of the things that.
Well, actually, going to locality, I could imagine because basically any matrix could be tridiagonalized. If we reduce to tridiagonal, we can imagine taking so a K Hamiltonian reducing it to a tridiagonal.
Yeah, but here all these properties depends also on the eigenvectors. So I wouldn't say that diagonalizing is probably not a legal operation in this business because.
No, all I was trying to say is that it's like, can you imagine open up model that it's not necessarily property?
Maybe not, because as I said, for these games, you need to choose a preferred basis. in all these games, you have to choose like the fundamental operators in our language. And that it's a notion that doesn't like a unitary change, doesn't like change of places. So yeah, I would be cautious.
So the last building block I would say is that, sorry that I'm introducing too many blocks here. Yeah, the parameterized support parameter circuits. So this is just a quantum circuit with parameters, and that's all. So why they are interesting? Because of course they can be built using quantum circuit nowadays. Of course, the current hardware is pretty noisy, but if your circuit is not really deep enough, then you can actually extract some of the property of the circuit from experiments. So this is the paper from Goober's common processor for random circuit sampling. And basically what they observed is that this, as I said, is Potter-Thomas type of distribution. So parameterized quantum circuit with, if you have a subtype of random parameter. So this single qubit has a parameter and they actually choose random. And in their case, the qubit gates are quite, they also have some parameters. So by using this parameter quantum circuit, they actually could simulate some type of behavior characterized by this Potter-Thomas distribution. So this is
so what are the squares?
sorry, where?
There are squares with two lines connected.
These are entangling gates.
They are like the C0 gates, the C0 gate, this kind of.
Yeah, but if you write down an equation for this,
so
what would it look like?
I don't really exactly remember the exact form of this, but it was more like here, it was block diagonal between block diagonal form, something like this. So here you have some type of unitary, but
so each block is a unitary 2x2 matrix.
No, so here 0, 0 actually goes to 0, 0, and 1, 1 goes to 1, 1. So they are not entangled, but 0, 1 actually goes to some zeta. 0, 1 I don't really remember the exact form of that, but So 0, 1, 0, 1, like that. So I think
So it's a rotation.
Right.
So spin rotation.
Yes, spin rotation. The reason why they use that is that because it is easy to be implemented in their
And that colored with the blocks was set. The blue one or the brown one and the green one.
Sorry, each one?
No, there you have vertical lines.
Vertical lines,
That one, for example.
Yeah. So they are those gates.
What gates?
This entangling gates. So these flats are entangling gates. So if the state was 1, 0, then they give something. And 1 here, if there were 1, 1, then it doesn't.
Okay. Let's see.
So let me switch gear to my work. So sorry, I introduced so many things. Even before I introduced my work, but let's jump to the instantaneous quantum polynomial circuit. So this was more like a simplified model for the quantum advantage. So what Google did is that support random circuit sampling. However, for here we have a bit of better understanding of the complexity. I will say you here. So the problem is really simple. So our quantum state is written like this. So here, this plus state is just a 0 with hardware. So I think it's right down. State is caret 0 plus 1. So here UD is the unitary, which is diagonal in this computational basis. And after that, you do one more hard work, and the output is just sampled in the computational basis. So UD is diagonal gate like this. And one of the examples is something like this. So this is a kind of just a classical Ising model over with the time evolution. So what is known is that you can actually prove under some of the observation. Yeah, it's rather also tricky, but yeah. But anyway, what you can do is that you can prove that the algorithm, the classical algorithm, the sampling from this circuit. So you can of course do it using quantum circuit. But if you have such an algorithm, the classical algorithm for doing the same task, then what is called is a polynomial hierarchy collapses, and it is a mild version of P equals MP. So a computer scientist doesn't really believe that it's true. So under this kind of assumption, you actually can say that the classical algorithm or something from this distribution doesn't really exist. Yeah. So your argument is a little bit involved.
Sorry, just to understand, you can go back to one slide.
Yep.
So by sampling, you mean that you want to find all the values of x1 to x5? Or what do you mean by sampling?
No, this.
Or
so you have a
distribution.
Px. So it is just a given by 1, 2, 3, 4. And the sampling means that you generate some samples x vectors like x1, xn, and let's say xp. And if you collect all these things and plot this distribution, like 0, 0, 0, 0, 2, 1, 1, 1. And you can have some kind of histogram, right? Yes. And if this is similar to Px, then you actually say that you sampled from the distribution.
So also that means that you have a bunch of components from x1 to x5.
Yeah.
So you map them to the real line first, then you find the distribution, or how are you going? What is the x-axis?
So just by collecting this, you obtain maybe another forward distribution, and the way to compare this is that, for example, distance measure. This is something called total variation distance, which is defined like this. By 2. So if this is small, then you have a distribution. You have an algorithm for sampling distribution.
And here the sampling is coming because the parameters theta are random, I guess.
Yes, theta is random. And for those class of problems. So this is a class of problems.
Okay.
Yeah.
So you say this quantum circuit creates the probability. If you measure for many realizations of theta the outcome of this quantum circuit, you will have effectively a way to generate numbers that are distributed according to the P.
Yeah. Okay. Yeah. And if you have a same algorithm classically, then
Sorry, another triviality. The theta are box distributed.
Theta, you can think about any other distribution, but in the original paper, I mean, in my paper, I assume that theta is from 0, just a random value from 0.
But roughly speaking, here, just want to do something that we know well. Here is a bit like when you want to sample according to a Gaussian and your random generator generates just a box, and you have to transform numbers that are distributed according to a box.
There can be one possible algorithm.
Okay.
Okay. However, like this computation complexes actually means that there is no any other like classical algorithm.
Okay.
Is there any like problems when one considers noise?
It's rather difficult. Yeah, I mean, there is actually the opposite proof that if you have a constant level of noise, then this problem can be classified easy. So yeah, it is still a high value. However, the point is that yeah, it is more like all this computational complex actually consider a class of problems. So if n is large and you have a constant small rate of noise, then it can be easy. But it doesn't really mean that the particular problem, like what Google did, is actually classified. So yeah, there is a concept between what people can do and it's proven. Yeah. Sorry. Yeah. So yeah. So the okay, yeah, the point here is that such a classical algorithm with anticoncentration. So anticoncentration, yeah, that's what I explained. So anticoncentration just means that if you just collect all these samples, then if this alpha probability, then yeah, if they are concentrated or like anti-concentrated. So that's also what anti-concentration means. So if you have a completely like a uniformly random distribution, then all your alpha probabilities at 1/2 to the n. So this is the case of this one. Yeah, uniform. And if you have a specific like a feature, for example, like if you have a distribution that px is 1 for when x is 0 and otherwise are 0. So it's just a concentrated distribution. Yeah, in this picture, you can just think about something like this. 0, 0, or otherwise 0. So if this is the case, then you say that it is a it is not anti-concentrated or concentrated. So yeah, what it is that both things. So the previous slide. So existence of classical algorithm with anti-concentration. So if one of the important question is that whether our circuit, even like here, satisfied this anti-concentration condition. Yeah. And anti-concentration is a necessary condition for the unitary 2 design. So if your circuit was already random, then it is automatically satisfied.
So because if C is 1, then it is uniform. So what is C when it is anti-concentrated?
Where is C?
On the left-hand side, you have C is equal
yeah. So
when
C is the arbitrary constant. So Z, yeah. So it is for Z another quantity. I have separately put down. So that Z is like square. Yeah. And if your distribution was just concentrated, then yeah, you have you have this G value like 2 to the minus n. However, otherwise, yeah, it's quantity. So yeah, but I would just recommend don't really think much about this because this is more like a proof that yeah, whether the distribution is unconcentrated or not, it doesn't really give any. Yeah.
So, but what is the value of C in comparison to the left figure?
Yeah. So if it is so uniform is so for example, like a C can be like a 2 or 4 or some just random like a value.
Okay, so what's relevant is the red part, the distribution.
So yeah, so
okay.
this is related to Px. Yeah. So if Px is right down like this. Okay. Yeah. Yeah. So yeah, what is true is that so for our so this R to R connected Hamiltonian or yeah, this R to R connected this gate. So of course, yeah, this you can think this is a Hamiltonian. Then the this anticoncentration. Sorry, this anticoncentration condition. This anti-concentration condition is satisfied, so there is a proof. However, for a sparse graph, so of course the problem is that if you have orthogonal connection, it's not really easy to implement using hardware. So instead, we want to think about our sparse graph. Like the connectivity is much more sparse. So see the IJ is only like between those graphs, not really orthogonal graph, not really over graph. So that's the main motivation. What it happens.
So in other words, you want to, let's say, okay, so you already know, let's say, again, in the same page, you already know that if the graph were a complete graph, you get the anti-concentration. Now, the complete graph is an horrible condition, hardware-wise, so you want to take a graph that is not complete, but still enjoy this property of being anti-concentration. Okay.
Or like in general, like not only the anti-concentration, but also or this complexity and this.
Okay.
So the first one I proved is that if it is too sparse, the graph is too sparse. So if the interaction is just too sparse, then it is classically similar. I didn't really define any graph yet. However, this is just a definition. So, you can just write down or this graph or these vertices, and for each pair, you just link them with probability Q. So this is this many graph, and the capacity is defined over this. If Q, the connection probability is less than 1/n, then it is efficiently classically simulable. This is based on some tensor network contraction algorithm. So basically this is a tensor network contraction algorithm. This quantity is rather like tricky, but what I proved is that this is bounded by logarithm. In my case, and because of that, I actually could contract this tensor network within polynomial-time, and you can actually simulate the whole circuit as classical.
So it cannot be anti-concentrated.
It cannot be anti-concentrated as well.
Otherwise, you violate.
Not really, because it also depends on another condition that of Shocking hardness, like whether computing the partial function of categorized inhibitors. So it is, but it is not really. So this is how the algorithm works. So first you have a graph, and this is the circuit associated with this graph. And if you write down it as a tensor network, then it is written like this. And by just looking at how tree width and this property actually works, you can actually prove that the circuit is classically similar. So
you're saying that, let's say, if the graph has only n edges, not enough.
It depends. What I proved is that Q is strictly less than n/1, and in this case, almost surely. So there might be some cases.
Sure.
That's okay.
Wait, there's only n edges of the graph.
No, rewired in some way. It's still random, but the number of. I think what is working on is. You rewire randomly, so you can have whatever geometry you wish. Well, even though, but anyway, let's say that you have whatever geometry you wish. But if the connections are only n, you don't have enough.
Well, but that is a tough constraint. Wire the graphs. I mean, it's basically you can go either from the ring to the star. When you have one side connect, so yes. It's a constraint.
Another possible property is that it actually makes some type of clusters.
You allow
Yeah,
So
it is a
graphs.
I mean, yeah, I don't think it's just a general random average training graph. And yeah,
Even the plus where it's
Yeah.
or star.
Ring or ring with a.
yeah, there were maybe some also isolated edges and another thing like that they are correct. Anyway, yeah, this is how I prove that. So I from the original graph make a circuit and transform it to tensor network, and this tensor network actually has a property that it can be simulated faster. So next, I also proved anticoncentration. Of course, I didn't really do from the beginning. This paper already proves almost the same result, but yeah, what I did is that extended to the random parameters through random uniform parameters. So in this paper, they only considered its connection zeta and all these things from 0 pi over n to pi over n. This discrete values of the thing.
Sorry, is distribution. We control the distribution between the
Yeah. So it is. And what I proved is that there is a constant. I didn't really give, but there is a.
So the probability goes like log n divided by n.
Yeah. And in this case, you can see a bit of like a complexities captured by anticoncentration. However, the real polynomial distribution actually requires a strong value. So this is our numerical research by comparing our probability distribution and real polynomial distribution, and yeah, this finite size scaling to mechanical 24. It is not really big, but it is bigger than usual manifold localization simulation. So I would say it's rather correct.
So n equal to 24. Does it mean that the Hilbert space is 2 to the power 24?
Yeah, that's right. So this is a straight for exponents and reading the search. Yeah. So by just increasing the connectivity, I actually saw different like this quantum chaotic behavior. So this is basically.
So the number of edges that you need is n log n. Because that is the probability for a single pair. So in total you have n squared pairs, I guess. So the number of edges that you need is roughly n.
Yeah, that's right. Okay. Q is the probability, the connection probability.
Probability that the pair is connected. So in total you have n square objects, and so overall you would connect n log n.
So yeah, so in quantum circuit, the main point is that people often consider that anticoncentration and polynomials are both actually from like a chaotic randomness or like randomness behavior. But if you really go deeper, then they have some type of different threshold. Yeah, okay. And let me go to the next part. Yeah, this is more close to what I already said in the CP, but yeah, let's go. Yeah. So the another property from quantum chaos of quantum circuit, basically from unitary 2 design, is that exponentially small gradient. So here gradient means that gradient of your observer with respect to a parameter of a quantum circuit. So if you just write a quantum circuit like this, and of course you can just group unitary like this, and you can compute this. However, if this unitary 1K, so if it's a part of unitary, satisfy unitary 2 design, then this gradient actually scales also inverse, doubly inverse exponentially. So it is just the same scaling with the out of time. This is always just from the property of unitary 2 design, but it's actually attracted lots of people because they want to argue that this parameterized quantum circuit cannot be trained well. So this is a numerical research from McLean, IBM guys from 2018. if you really Google this, you will be really surprised. It's from 2018, but it is cited more than like 4,000 times. Yeah, it's a really incredible number of times because there is a quantum hype. It's really less what it really is. Yeah. Anyway, yeah. So this is the number of qubits, and y-axis is they actually made their own network, this parameter quantum circuit, and they computed the gradient of the first element. And it's basically the square root of the case exponential. So that's what they showed. So because it gained lots of the fraction, people also studied when it happens and when it's not. So post-functional locality is first considered by Serrazzo and other people. And yeah, in some certain case, local observable doesn't really give exponentially small gradient, but they are still pretty small. And if you have a large number of qubits, it can be still too small. And there is a kind of quantum circuit, and that's not really like a 2D local circuit. You can think about some sort of quantum convolutional neural network, which resembles this meta type of tensor network. And in this case, people actually could prove that this exponentially small gradient doesn't really exist. But still, we don't really know yet whether this convolutional neural network is really useful for any other problems. Yeah. And there's also like a paper by some Chinese guys related to initialization. So how you initialize your network, how your circuits, and just with some architecture actually give you known exponential small gradient number of qubits. But their research actually still say that the gradient is exponentially small with the circuit depths, and they are I think they are not that useful. So before going further, I mean, all these things are basically how to avoid unitary design of your parameter quantum circuit. So by just constraining something, you avoid this too much chaotic behavior in your quantum circuit and can have some controlled behavior. So that's basically what they do. And my work is also in the same line, but I more consider this so-called quantum circuit ansatz, so-called Hamiltonian variation ansatz. So in this particular ansatz, what we do is that we have a particular Hamiltonian and we want to solve that Hamiltonian. So this Hamiltonian has a parameter and some what I mean solve is that find the ground state of this Hamiltonian for some given tau. By just decomposing this Hamiltonian like this, and with this property, you can construct this circle like this. So from the given state, you evolve into the first term and second term and so on, and repeat this p times.
So why can that be done? Why can you write the Hamiltonian as a sum of commuting terms?
It's always possible because
you can write the sum of itself. Then it commutes.
But in this case, for example, like I don't know if it's possible for this for the fermionic Hamiltonians, but for example, for spin Hamiltonians, you have it is sum of Pauli strings. You can decompose it to Pauli strings, which actually for example, like x, y, something like that. Always like so there are 2-to-the-n possibility, 4-to-the-n possibility of these Pauli strings, and you can always write down them, and you can just group it with x1s and y1s and z1s, things like that.
Because if they are commuting mutually, you can diagonalize them.
Sorry. So it means that not they for different k are commuting. What I mean is that sorry. Let's also say transfer field eigenmodel. One is this one. two. They have n terms, but it comes inside of this Hamiltonian arbitrary. So that's what I do. So here, like that's one, and that's two. It's in here, two, three. It's also here and there. And to be honest, it is not really like strictly necessary, but it's just a usual. Better to shoot this. Then what we have is that the using adiabatic theorem, it is guaranteed that this specific parameterization actually can give you the ground state for any tau. Yeah. So from tau equals 0 and tau equals t, yeah, you can think about this adiabatic evolution, and by totalizing them, they have exactly the same form. However, what you do is that just a change in totalization, they have a specific just a value. However, by changing this value to the parameter, what I hope to have is that you can observe it with a shorter depth circuit. And for this specific ansatz, people also have seen this type of barren plateau, so a simple quantum chaos. So they are not really intuitive design, because if you look at it carefully, then they have some type of symmetry. However, within that symmetric vector, what people found is that they are quite random, quite behaving random. So that's what I have seen. So what I basically showed is that by restricting the parameter, I can make HVA as a Hamiltonian evolution. And as we observed from the out-of-time correlator, we can make it avoid from unitary design. So that's basically the strategy. So yeah, basically what we had is that something like this. The gradient is this, and we specifically consider the case whether unitary is approximated by Hamiltonian evolution, and where H is a local Hamiltonian. So yeah, for short time evolution, we can actually prove that, but for short time evolution, yeah, you can think it is much more identity, and the initial value just comes out, and you can, of course, you can deviate from your chaotic reason. Of course, it's much more simpler. However, more interesting thing is that, yeah, even for large T, if your unitary is approximately long time evolution, you can say that it is actually part from the real parent unitary. So this is our numerical research. Yeah, so what I did is at first find the lower bound of this gradient quantity, the magnitude of gradients, and simulate it using a random local Hamiltonian. So for random local Hamiltonian, I generate randomly from using my computer. I computed the exponential to the minus I8t, and yeah, if you compute the average value over t, then this is the lower bound, and I just put my result to this, and this is the computed lower bound. And it's rather tricky, but so it is number of qubits, and this is the lower bound of the gradient magnitudes. And yeah, it's rather tricky to say that it is really like a non-exponential. However, if we impose the time reversal symmetry to the Hamiltonian, it was rather like a more uniform. And basically, because I believe the universality of simulation, I would say this is also not really exponentially small. Yeah. So this is what I observed for numerically. And the last missing factor is that how we approximate our HVA via some evolution. The first log is that this blocking magnetic expansion. So for the HVA, when the parameters are small, we can always approximate it as Hamiltonian evolution. So yeah, this is just possible by blocking magnetic expansion. And by repeating them, and by repeating them r times, we can also express this particular circuit as a Hamiltonian evolution for some local Hamiltonian. Yeah. So by this strategy, we could actually make the gradient really exponentially small. So this is actually random parameters, and for the in this Ansatz, I just put random parameter theta. So one possibility is that just to theta from random value from 0 to 2 pi, and another one is that just really put this constraint to make it approximate to this. And I compare the nature gradient here, and you see that they actually with my constraint, the gradient doesn't work. Okay.
So maybe I missed like the intermediate, like some slides. So are you saying that if I have a Hamiltonian variational Ansatz, I do not have parameter for any cost function and any chosen?
No, it's in my case, what I say is that you can find the initialization or like find the particular parameter set that HV is pretty complex. So if you have a let me go a little bit. So this is a paper. They also use the Hamiltonian variational Ansatz, but they observe the barren plateau. So if you just put random parameters on your Hamiltonian variational Ansatz, then the gradient is exponentially small. Yeah. However, if you constrain the parameter, then you can be our circuit can be deviated from this chaotic rhythm and can be more like a went to the reason that can be approximated by local Hamiltonian evolution. And local Hamiltonian evolution, because they preserve energy, they can be distinct from pure quantum chaotic behavior. And that's how I observe more like constant gradient. Yeah.
So how do you set the feature? Did you say how you find the initialization?
Yeah. So this parameter set is more determined by this blocking mechanism extension. So if your parameters are sufficiently small, then it is well approximated by this local Hamiltonian evolution.
But then if I'm just doing say BQ like that one, how do I set up?
So this is the of course, this is the result here. I can go down a little bit. There is a hidden slide. Yeah. So this is only for the initialization. It is more like for the initial short time initialization, and for the so this is just a random initialization. And the second one is that the parameter condition that actually satisfies this blocking mechanism condition can be approximated by short time evolution. And the last one is that just for small epsilon, so independent to m. Yeah, and in this case, we observe the gradient actually scales like this. So these solid lines are for our initialization. Yeah, well, of course, y-axis is the magnitude of gradient, and it's never the case. And for other initialization, it's actually the case. So
okay, so you mean so suppose I want to solve a generic cost function, then maybe what I can do is just use small.
But more like a scares with the more like a scares with the 1 over n. So here, for example, like this is the parameter condition I use. Yeah, so basically that's all my term. Yeah. And basically what I did is that the random circuits are often too chaotic. And what I did is just by adding some constraints, it can be approximated by local Hamiltonian evolution, which is less chaotic, and it prevents this variable. Thank you so much.
Okay, we already had several questions during the talk, but let's see.
Yeah, sure.
Maybe one more here. So I remember like we had Cole, and he has also a paper using planning to V algebra to
Yes.
study to avoid invariant clause for HVA.
Yeah, that's true.
Are the results consistent?
Yeah, results consistent. So in our case, we actually need to change the dynamic Lie algebra to the vector space dimension. But yeah, the point is that the local Hamiltonian, they are vector space. They are not really closed dynamic Lie algebra. However, yeah, by just changing the definition or result consistence. Yeah.
So in the world where I come from, quantum K is always defined in terms of level correlations. When they are given by random matrix theories, quantum chaotic. But you didn't mention that. Why is that?
You mean random matrix theory or?
No. If the levels of system,
right. Yeah, that's right.
are given by
so okay, yeah, sorry.
Matrix,
I actually wanted to add the slides, but yeah, I just forgot. So the point is that if you have a Hamiltonian, which is run randomly.
No, I'm thinking of a non-random Hamiltonian. For example, the Hamiltonian of a sinusoidal.
Yeah.
If you look at the levels of
it's
correlated.
That's right. Yeah. So they're consistent. However, the interesting point is that if you see the eigenvectors, then they are quite different.
No, not for the.
I mean,
sinusoidal.
Yeah, it depends which property you are working at. But for example, if you have a random Hamiltonian, then they don't have locality, and that actually makes this eigenstates a bit more deviated from the local Hamiltonian eigenstates. So one of the.
But then there are no chaotic systems because for all specific systems, the eigenvectors are very. We only define them in terms of eigenvalues. But for generic systems, eigenvectors are always completely different.
Yeah.
Each system has its own eigenvectors. And it is hard to say if it's quadratic, probably they are distributed all over the system.
So, yeah. Okay. I don't really have a full answer, but for example, like in our workshop, Yosuke Hamazaki actually he introduced this atypicality of operators, and that's kind of related to the I mean, basically the point is that when Hamiltonian, local Hamiltonian and non-local like a random Hamiltonian, if you see the level dispersion or something like that, then they show actually quite similar behavior. But if you really work with the eigenvectors and all these other properties, then they somehow show some deviations. So that's one of the interesting part for me. I mean, if you ask how much different they are, then I don't really have a right answer. Yeah, thank you.
Yeah, maybe I can resolve the question. In this procedure in which you introduce the constraints, so you keep the gradient big, you lose a little bit of specificity, I guess, right?
Yeah, maybe that can be true.
So my guess is that is good because you are still trying to simulate an area law.
I mean, it is not really area law. It can approximate long-time evolution of local Hamiltonian, and it actually.
No, but you want to still simulate. You want at the end still approximate the ground state.
Yeah, that's right. That's right.
So, and this ground state that you want to express, I would say, is an area law.
Yeah,
if this constraint will be okay if you want to approximate a state that is not.
I mean, Yeah, in general, I mean, in the paper, I actually said that I can use it to simulate Hamiltonian dynamics, of course. But yeah, I never really have thought too much about observing the ground state. But I would say that
because you run this for random, let's say, values of the parameters, and you just check.
Yeah,
okay.
I didn't run the full PQC simulation for this. Yeah, I mean, I have done for the initialization, but not for this long time ago. Yeah.
Would be interesting maybe, because I suspect that it will work if you are trying to simulate an area law system.
Yeah, maybe.
If you try to simulate the volume law, probably.
I mean, So. What I proved is that this actually can simulate volume law state, but it doesn't necessarily mean that we have a full express state.
Yeah.
But anyway, I'm satisfied with that. But there might be some more details.
I'm not saying that they should. Okay. If there are no more questions, we can probably thank Chae-Yeun again for this talk.
I mean, despite of heavy rain,